I want to deal with a couple of unusual cases. But we're not going to solve these problems all the way through. I just really want to show you how you would set them up. As you can see, it takes a very long time to solve all these problems all the way through. So I'd imagine everyone's attention span for this is probably wearing pretty thin. Let me just show you the special cases. So first thing is we've said that in order for this technique to work, the degree of the numerator has to be less than the degree of the denominator. So the question is, what if it's not? What if it's greater than or equal to the degree of the denominator? The answer is that then you have to perform polynomial long division. So here what we have is we have the integral of x cubed plus 1 over x squared minus 4. So what I'd actually have to do is divide x cubed. I'm going to write this out the long way. 0x squared plus 0x plus 1. I'm going to divide that by x squared plus 0x minus 4. And some of you may remember your polynomial long division. What I have to do is ask how many times x squared goes into x cubed, and then I'll use essentially the ladder method that you all learned in probably second or third grade to subtract. So now it goes in x times. I'm going to multiply the expression out here by x, giving me x cubed plus 0x squared minus 4x, and then I subtract. So this gives me 0, 0, and then 0 minus negative 4 is 4x. 1 minus 0 is 1. So what I have here is I have that this is actually equal to the integral of x plus 4x plus 1 over x squared minus 4 dx. So now, and I can break this up, this becomes the integral of x dx plus the integral of 4x plus 1 over x squared minus 4. So now what I have is I have this relatively simple integral that I can do, and then I have this one that I can do by the techniques that we've been talking about. And by the way, when you set that up, of course, keep in mind that 4x plus 1 over x squared minus 4 is equal to 4x plus 1 over x plus 2, x minus 2. So what I actually have here is just a polynomial over two linear factors. So what I would do is I would find this antiderivative here just by ordinary, by the ordinary power rule for antiderivatives, and then I'd use partial fractions on this part here. So again, I'm not going to do that, but that's how you would set this up. So what if the denominator contains a reducible quadratic factor? If you look at this integral here, I forgot the dx, there we go. If you look at this integral, it looks like what we have is a linear factor and a quadratic factor, but actually we don't. The reason for that is that if you look at this, so well, actually, let me show you what the wrong thing to do. The wrong thing to do would be to say a over x plus 3 plus bx plus c over x squared minus 9 equals 18 over x plus 3 x squared minus 9. This is wrong. So, and it's wrong because the rule about quadratic factors that you see here only applies when the quadratic factors are irreducible. In reality, 18 over x plus 3 x squared minus 9 is actually equal to 18 over x plus 3 x plus 3 x minus 3, because this is the factoring of that expression. So this is actually equal to 18 over x plus 3 squared x minus 3. So the interesting thing is it looked like we had one linear factor and one quadratic factor. What we actually have is a repeated linear factor and then a non-repeated linear factor. So the correct decomposition of this is a over x plus 3 plus b over x plus 3 squared plus c over x minus 3, which, as you can see, is quite different from what's sort of the naive guess as to what the decomposition was going to be. So you do have to pay attention to that issue, and just notice that not every time, it's not the case that every time that you see x squared in the denominator that you have a quadratic factor. It's only irreducible quadratic factors that have this special rule. And then, of course, in this case, they combined with one of the linear factors in kind of a surprising way. And then finally, we deal with the question of what if the denominator has a repeated irreducible quadratic factor? And the answer, of course, is that we have to repeat its existence in the decomposition. So here what we have is we have a single linear factor, which is x. X is a linear factor because x just equals x plus 0, so it is a linear factor, and people often miss that. And then here we have a repeated quadratic factor. It's repeated in the sense that it's a quadratic factor, it's irreducible, and then it also has an exponent of 2. So the correct decomposition of this is a over x, that's how you deal with the linear factor, plus bx plus c over x squared plus 2. And then since the quadratic factor is repeated, we have dx plus e over x squared plus 2 squared. And we set that equal to 4 minus x over x squared plus 2 squared. So that's the correct decomposition for this integral here. So you do have to pay attention to the possibility that a quadratic factor is repeated and would have to be dealt with in this way. This is a very long problem to solve because you have 5 different constants, and one of the terms is going to involve a trigonometric substitution in order to integrate. So okay, anyway, those are sort of the weird special cases you do have to pay attention to. Finally, let me ask you about this, or at least you may be asking yourself this, which is what if you can't even reduce the denominator to a quadratic? In other words, fortunately, the answer is, this is the good news, there is no such situation. It's basic theorem of algebra. It goes a little bit beyond this course, but it's basic theorem of algebra that any polynomial can be factored as a product of linear factors and quadratic factors. There's no such thing as a cubic, let's say a third degree polynomial that can't be factored using linear or quadratic factors. Just here's an example of that. You might see something like x cubed plus 8. It looks almost like it would be irreducible, like an irreducible cubic, but actually this can be factored. If you remember the sum of cubes factoring formula, this can be factored as x plus 2, x squared minus 2x plus 4. So as you can see, this can be factored as a sum of sorry, not a sum, as a product of a linear factor and a quadratic factor. So you never have to worry about that situation.